Hello to all of you, dear students. This is Tamás Jávor. Welcome back to Rubber Duck Physics. Today, we are going to explore another key concept in rotational motion, torque. Just like forces make objects move in a straight line, torque makes objects rotate. It's not just about how much force you apply, but where you apply it. That also matters. Let's start by defining torque. It sounds like the name of a lower-level hero or maybe anti-hero from a fantasy film, doesn't it? Torque is the turning effect of a force. It's what makes objects rotate around the pivot point. In some books and curricula, it's called the moment of a force, but we'll stick to torque, which is what the DP syllabus uses. Imagine you are using a wrench to tighten a bolt. If you apply force farther from the axis, it's much easier to turn the bolt. The same thing happens when you open a door. The farther away from the hinge you push, the easier it is to rotate the door. Torque is determined by two things: the force you apply and the distance from the axis of rotation to where the force is applied. However, examples like these, doors and wrenches, aren't great for understanding what happens when something spins up or accelerates rotationally. Why? Because in these cases, friction and other forces oppose the rotation. So we'll use them now to introduce torque, but later we'll explore better examples for understanding dynamic motion. Here is another real-life example, using a spanner or a socket wrench. If you are using a longer spanner, it's much easier to loosen or tighten a bolt. That's because you are increasing the distance from the axis of rotation. When you use a longer spanner, you generate more torque with the same force. This is why mechanics, I mean those hands-on people now, not the area of physics we are studying, often use long spanners when dealing with tight bolts. There are two ways we can think about the formula for torque, which is tau equals R times F times sine theta, where F is the force applied and R is the distance between its point of application and the axis of rotation, while theta is the angle between R and F. Both of these interpretations help us understand how torque works geometrically. First interpretation, focus on the force. The sine theta represents the component of the force that's perpendicular to R, the straight line between the 2 points mentioned. So if you push the wrench at an angle, only the perpendicular part of the force contributes to the torque. Second interpretation, focus on the distance. The sine theta can also apply to the distance. Multiplying it by the sine value, we get the so-called lever arm, the shortest distance between the axis and the force's line of action. This distance shrinks or grows depending on where and at what angle you apply the force. These two ways of thinking help us understand how forces make objects turn. The result is always torque, the turning effect. Now, let's explore what happens when you apply the same force to an object that can rotate around a fixed axis, but at different angles. We'll start with the maximum possible torque. Here, the force is applied perpendicular to the line between the point of application and the axis of rotation. This produces the maximum positive torque, making the wrench turn counterclockwise easily. When we decrease the angle to, say, 45 degrees, the torque decreases. The wrench becomes harder to turn, or the force may not even be enough to overcome friction because the force is no longer perpendicular. If the angle between them is larger than a right angle, let it be 135 degrees, because of the symmetry of the sine function, the value of the sine is the same as for 45 degrees, therefore, the same amount of torque will be exerted as with the force being at 45 degrees. We apply the force directly along the wrench handle, theta is 0 degrees, either pushing toward or pulling away from the pivot, there is no torque. The wrench doesn't turn at all. And if I reverse the direction of the force, applying it perpendicular in the opposite direction, the wrench rotates clockwise, producing maximum negative torque. Speaking of that, let's talk about positive and negative torque. If you apply force in a way that makes the objects rotate counterclockwise or changes its ongoing rotation towards the counterclockwise direction, the torque is positive. If the force makes the object rotate clockwise or changes its ongoing rotation towards the clockwise direction, the torque is negative. The direction of the force and where it's applied determine whether the torque is positive or negative. What is the unit of torque? Well, it gets created from the units in its definition. The unit of force, Newton, times the unit of distance, meters. The value of the sine function is a simple number. It multiplies by just 1. Does this sound familiar? Or perhaps if you decompose a Newton into kilogram meters per second squared? Pause the video, close your eyes, and try to remember where you have seen such a unit. Probably found that the unit of work and energy, the joule, seems to have been defined the same way. However, I have sad news. It is only the algebraic form of the two definitions that are alike, and they are completely different units. After all, when defining work, we multiply the force and the distance that were parallel, while in torque, they are perpendicular. Moreover, in the definition of work, that distance could be just any value moved, while here at torque, it is strictly one value, the length of a line connecting two fixed points. So, meet the different unit of torque, which is the newtonmetre. Nobody gave it a fancy single name after any scientist yet. Maybe if you study hard and become a renowned researcher in physics or engineering, you could have the newtonmetre replaced by your family. To understand how torque causes objects to spin faster or to accelerate rotationally, we need to look at objects that can freely rotate without being stopped by opposing forces. So, in our later videos, we will explore examples like rotating wheels and spinning disks, which will help us understand how torque and angular acceleration are connected. To get prepared for the next video, imagine you are tightening a bolt with a wrench. You push on the wrench, but you are, or your opponent is, also holding the bolt steady with another tool. If the turning effect of the two forces balance each other perfectly, the bolt doesn't turn. Why does this happen? What does it mean when torques balance out? When torques balance out, an object is in rotational equilibrium, meaning it doesn't rotate. In our next video, we'll explore the conditions needed to keep an object from rotating and how equilibrium plays a key role in both linear and rotational motion. This time we have learned how torque makes things rotate. But the next question is, what happens when you have multiple torques acting on the same object that is able to rotate? Let's dive into that in our next video on rotational equilibrium. Enjoying these videos? For even more support, I am available for online tutoring across IBDP Physics, A-Level Physics and Math, and AP Physics. My contact details are in the channel description on the Rubber Duck Physics YouTube page. Be sure to access it on a web browser. Drop me a message if you would like to arrange a lesson. Thank you for watching this video, and see you next time.